is Spacelab. To understand how it got there, we must look at the specific geopolitical needs that forced a fragmented Europe and a resource-constrained NASA to collaborate. Under a formal 1973 agreement, European nations took on the funding, design, and construction of Spacelab. In exchange for delivering the flight units, NASA provided the launch vehicle and guaranteed flight opportunities for European astronauts. This chart outlines the economic problem NASA faced. Launching single-use satellites for every microgravity experiment was prohibitively expensive. NASA needed a reusable, modular laboratory housed inside the returning shuttle, one that allowed civilian scientists to conduct research in orbit without spending years training as career astronauts. Across the Atlantic, European nations faced their own pressures. Following a series of early launch vehicle setbacks, they sought a fast-track method to establish a human spaceflight program. A joint project of this scale provided the necessary structure to unite their diverse aerospace industries. These intersecting needs culminated in a 1973 Memorandum of Understanding between NASA and the European Space Research Organization, the predecessor to the European Space Agency. This agreement established the technical and financial integration required for a shared transatlantic space infrastructure. Spacelab was engineered to rely entirely on the Space Shuttle for transportation, electrical power, and life support. Without the orbiter, the laboratory had no way to function in space. The primary component was the pressurized module. This 75 cubic meter cylinder provided a controlled, shirt-free working environment in low Earth orbit. Inside, the module featured a removable floor and standardized science racks. This modular interior meant experiments could be easily swapped between missions. For instruments requiring direct exposure to the vacuum of space, engineers designed unpressurized external pallets. An access tunnel connected the main module directly to the shuttle's crew cabin. Building this hardware required a massive manufacturing effort across 10 European nations. Contractors manufactured specific subsystems before assembling the final racks and frames. Once complete, the European Space Agency handed the flight unit to NASA, shipping the massive components via military transport plane to the United States. At the Kennedy Space Center, technicians carefully lowered the European module into the American orbiter's cargo bay, connecting the myriad data and life support interfaces. The successful delivery and integration of European hardware enabled the shuttle to support a diverse range of laboratory-based investigations in low Earth orbit. 10 years of development culminated on November 28, 1983, with the launch of the STS-9 mission aboard the Space Shuttle Columbia. Columbia carried a 6-person crew into orbit, the largest single crew in the history of spaceflight up to that point. Among them was physicist Ulf Merbold. Flying as a payload specialist, Merbold became the first ESA astronaut and the first non-American citizen to fly on a NASA space mission. To maximize their time in orbit, the crew operated at an intense tempo. They divided into red and blue teams, working staggered 12-hour shifts, to conduct science 24 hours a day. Inside the module, researchers floated in microgravity, working directly with advanced medical and biological experiments in a spacious, fully equipped laboratory setting. Over the course of the mission, they executed more than 70 distinct experiments, spanning plasma physics, material science, and deep space astronomy. Meanwhile, the Payload Operations Control Center in Houston maintained a continuous data and video link, allowing principal investigators on Earth to interact directly with the astronauts running their experiments. After 10 days and 166 orbits, Columbia returned safely to Earth, touching down on the desert runway at Edwards Air Force Base. The mission validated a model of orbital research where civilian scientists and international hardware operated as a single cohesive unit. STS-9 was the proving ground for a program that eventually included 22 dedicated missions between 1983 and 1998. Spacelab's modularity allowed NASA to fly diverse configurations tailored to specific scientific goals, including pallet-only missions where instruments were directly exposed to the vacuum of space. These later missions utilized specific hardware advancements developed under the Spacelab program, such as the instrument pointing system, which allowed for high-precision deep space and solar astronomy. As the flights continued, Spacelab provided European nations with the practical experience in astronaut training, payload integration, and human spaceflight operations they had initially sought. The physical engineering of Spacelab heavily influenced the design of future space habitats. Its foundational pressure shell design and standardized science racks were directly adapted to build the next generation of permanned orbital outposts. We can see the ultimate evolution of the Spacelab concept today in orbit, functioning as the European Space Agency's Columbus laboratory on the International Space Station. The Spacelab program produced the engineering blueprints and international protocols that eventually made the International Space Station a viable project. For more on the engineering that built the space age, you're watching Cosmora HQ. Like this video, comment below on which Spacelab achievement you think mattered most, and subscribe for more evidence-led space documentaries.